Hello, this is Mr. McGovern, and this is the second video in the Unbalanced Forces series, where we're looking at linking motion maps and force diagrams. So in the first video, the last video, we looked at Newton's second law, and the summary I left you with was that there's a formula for Newton's second law, and the way I like writing it is acceleration is due to the total force on an object divided by its mass. And the other important point I had was that the direction of the total force is always the direction of the acceleration. So I want to explore that, and I want to explore that using motion maps, which we've done in the constant velocity and acceleration video series, and force diagrams. So the video that I had last time, I'll play it again, was me using this this dummy here to apply a force to the right, and you see the box start speeding up. You can see at the top the speedo, the box is increasing in speed, so it's accelerating. Then I slowly decrease that force and apply a force in the opposite direction, opposite to its travel, and we see that the box slows down. So let's look at this in depth. So to start with, when I was applying the force to the right and the box was speeding up towards the right, let's have a look at a force diagram. The first thing we do is identify the system. So let's just think about the box. And we draw it as a dot. There's a downwards force due to gravity from the earth, and there's an upwards force, it's a normal force from the skateboard on the box. Then there's a force to the right, which I've called an applied force. Following our convention of the names of forces we've got, we don't have one called applied force. It's actually a normal force. And the reason it's a normal force is it's 90 degrees, normal means 90 degrees to the surface, and the surface is the hand. I push with my hand, you imagine putting your hand out flat like that, and then 90 degrees to that is the direction of the force. That's a normal force. You notice I've got my equality signs for my upwards force, my downwards force, they balance out. So I'm only left with a force to the right. And that is my total force. The total force is towards the right. I can then draw a separate motion map. Always with motion maps we start with a coordinate system. I've chosen mine to go to the right because everything's pointing to the right. So that's my positive direction is right. My velocity is increasing, so those velocity arrows get bigger and bigger, and the dots get larger and larger distance between them. And then my acceleration arrows are effectively the difference between two velocity arrows, and they are both pointing to the right. I need a right pointing acceleration arrows to make each of my velocity arrows bigger and bigger and bigger. And so what do you notice? My acceleration is pointing to the right, and my total force is pointing to the right. The acceleration and the net force point in the same direction. So what about when I was moving to the right, but pushing it to the left and it was slowing the box down? What about then? So identify the system, draw my force diagram, my up and downs don't change, but now I have a normal force from the person, or the hand, pushing towards the left. And therefore that is pushing towards the total force, or the net force is pushing towards the left. I'm still going to keep my coordinate system choosing right to be positive. If you notice on the video here, on the screen grab from the video here, I'm applying a force of negative 70 newtons. Right? It's negative because they've also chosen right to be the positive direction, and so when this person is pushing to the left, it's pushing in the negative direction. So they've applied negative 70 newtons. So that matches up with my coordinate system. My velocities, box is still heading to the right, but slowing down. So each of these arrows gets smaller. So what do acceleration arrows look like when the velocity arrows are getting smaller? They point the opposite way. Okay, because if they were pointing to the right, my velocity arrows would be getting bigger. So I now have my acceleration arrows pointing to the left, my net force also pointing to the left, and once again, it doesn't change. The acceleration and the net force point in the same direction. So in summary, this is always true, and it's the acceleration and the net force always point in the same direction. It falls out of Newton's second law, but many people ignore the second point and just want to do a calculation. Motion maps, especially the acceleration from the motion maps, they can help you with the force diagram. Right? It might be that you might want to draw a motion map first to figure out what's happening to the acceleration. That'll give you an idea. I know the net force therefore must be pointing in the left direction, just like the last one. And the opposite is true. Let's say you draw a force diagram first and get the net force. That'll help you decide and know which way the acceleration is pointing as well. So I've always said motion maps are so important, and they're going to keep showing up and up and up. They are a very good tool for conceptually figuring out what's going on in physics situations.